data. Let me first tell you the meaning of what we want to do today. Every statistical model has assumptions, right? If you look at what we did in the linear regression model, we have a way to revisit and investigate whether assumptions are met, right? What if in a situation where assumptions are violated? Of course, you know what we did, right? We basically used transformation, right? Also, in analysis of variance, okay, so, we also have assumptions of constant variance, which we call homogeneity of variance. We also have normality. And so on like that, we have a way to investigate that. And the moment the assumptions are violated, what are we going to do? Now, what we want to do today, when you are working with the analysis of variance and assumptions are violated, then what we need to do, we need to transform our ANOVA data. That is what we want to do today. We need this particular topic if there's a violations. But you know what? If everything is good, if there's no violation, we don't need this. Okay, and that is what we call transforming ANOVA data. But let me tell you this. If you look at what we did in analysis of variance, we use analysis of variance in a situation where the response variable is continuous and we have a categorical predictor. Okay, when you have one categorical predictor, that's a one-way ANOVA, right? When you have two categorical predictor, that's a two-way ANOVA. When you have three categorical predictor, that will be three-way ANOVA. And you know what? I remember I walk you through two-way ANOVA without interaction. We also did two-way ANOVA with interaction. But let me tell you this. Irrespective of the type of ANOVA you are dealing with, all of them, they have assumptions. If assumptions are violated, what are we going to do? Okay, because according to Fisher-Ronald, 1926, okay, the Fisher-Ronald said, because the Fisher-Ronald was one of the founder of analysis of variance, and he said when assumptions are violated, if you conduct an ANOVA test, you're actually going to mislead. I'm going to say that again. When assumptions are violated and you ignore that and you go ahead and conduct analysis of variance tests, he said you're actually going to mislead. Okay, and that is the reason why we needed to investigate whether assumptions hold or not. Now, what if in the situation where assumptions are violated, then we need to transform our ANOVA data. Okay, now in the outline today, I'm actually going to walk you through different type of transformation. You remember we did that under the linear regression as well, right? We could have a log transformation, right? Square root transformation, right? Reciprocal transform. There are different kinds of transformation. We basically want to look at the one that will work at the end of the day. Now, I'm actually going to show you, there are two special way of transforming ANOVA data. The one of them is the Tukey. We call it Tukey-transformed. Tukey-transformation. Then we have a Box-Cox transformation. Do you remember in linear regression, we actually use, you get a point we use a Box-Cox transformation where we actually estimated optimal value of lambda that can actually bring the distribution of the response to normality. Okay, so I'm going to show you how that works today. Okay, now let me tell you this. For instance, maybe we are working on a turbidity data, turbidity. Turbidity data is one of the environmental data. And I want to tell you this. Environmental data are not normally distributed. Okay, they used to be skewed. When the distribution of data set is skewed, then there's a violation of normality. You know why? Because when the distribution of the response variable is skewed, automatically the probability distribution of residual will also be skewed. I'm going to say that again. You know, what happened what happened to the distribution of the response variable will also affect the distribution of the residual. You remember that if you really want to investigate, we normally investigate the probability distribution of the residual, because in statistical analysis, the two of them, they should have the same probability distribution. The probability distribution of the response and the probability distribution of the residual have to be the same. But I want to tell you this: the moment the probability distribution of the response variable is not normal, then the probability distribution of the residual will not be normal. I'm going to say that again. Anywhere in the world, it is statistically proved and mathematically observed that if the probability distribution of the response variable is not normal, then the probability distribution of the residual will not be normal. Now, and that was, look at what I want to talk about now. I want to talk about water quality, the quality of water that we drink, right? Okay, and I want to look at the turbidity. Turbidity is a measure of how cloudy water is due to suspended material in the water. Okay, so water quality parameters such as these are often naturally log normally distributed. Take a look at that. Water quality is an environmental data. They don't normally follow normal distribution. You know what we need to do before they can be normally distributed? We need to take the log. We need to take the logarithm of that before they could be normally distributed. Okay, so, but occasionally high or very high, you know? So, and that is the reason why performing analysis of variance of such could be misleading, because there's going to be a violation, because environmental data, they don't normally follow normal distribution. Okay, now, this is the data set that we have for the turbidity. Okay, we collect, if you take a look at this data set, if you plot the histogram of this data set, okay, this is a response variable. Okay, if you plot the histogram of this data set, you're basically going to have this. What do you see? This is not normally distributed. And you know why? You know, this is not very surprising. You know why? The reason why this is not very surprising, because environmental data are not normally distributed. And for you to use analysis of variance, what is the requirement? The requirement is that the sample that you choose from each group has to be what? Normally distributed. Okay, so this is to show you now that it is not normally distributed. Okay, now this is the histogram. You can also look at the Q. You can look at the normal QQ plot of that and see. Take a look at that. This is an evidence that the turbidity data, which is a measure of water quality, is not normally distributed. Take a look at that. Okay, this is actually showing that it's not normally distributed. Okay, now, you know, what we basically want to do now, you know, there are different kinds of transformation. Okay, when it is not normally distributed, one of the intervention could be, oh, let's take the square root. Okay, what am I doing here? And look at SQRT turbidity. Okay, maybe you know why? Well, I want to take the square root. I'm going to show you. When you take a look at this guy here, right? It is skewed to the right, right? You know, it's moved to the right. Okay, now you need to use a compressor to let it back to the middle, right? It is far away to the right. Okay, in mathematics, if you want to make a huge data to be small, what are you going to do? You can take a square root, you can take the log. Because logarithm of a number will be very, very small, right? Now, that is the reason why here we're basically taking the square root. And after taking the square root, look at that. After taking the square root, we draw the histogram again. Okay, why are you drawing the histogram again? You drawing the histogram again, you basically want to see whether you know, the intervention has worked. Okay, this is a square root transformation. And take a look at what we have now. This is a little bit better, right? This is a little bit better, but this is not, exactly normally distributed, but this is a little bit better than what we had before. Okay, now another thing we could do. This is another transformation. The transformation we did before was to take a square root, right? But look at this transformation. You know what we actually want to do? We want to take a cube root. Cube root. There's a different in mathematical analysis. If I write it the square root of y, I can decide to take a cube root. Okay, so each of these is still a way to transform the data. Take a look at what we're doing right here. We are trying to take a cube root, and we draw the histogram again. Now, this is what that gives us. Okay, it is not a transformation effort. It is not every transformation effort that work. Why are we drawing the histogram again? We basically want to see whether it's going to give us the shape we want. What is the shape that we want? Normality. That's what we want before we can proceed using ANOVA. Okay, so take a look at this guy now. It is not normally distributed, even though it is a little bit or better than the distribution of the original data set. Okay, now another transformation effort. Look at what I'm doing now, log. You know what I've done today? We tried square root. We've tried cube root. We're now trying log. Whether you're doing the square root or you're doing the cube root or you are doing the log, what are you trying to do? You are compressing. We actually apply those transformational technique when you have when the distribution of the data set is skewed to the right. Okay, when it is skewed to the right, you actually want to bring them back to the center. This is it. This is the center, right? Maybe it is skewed to the right. You now want to bring them like back so that the stay here and the stay here, they're basically going to be the same. Okay, now when you take the log, we're going to draw the histogram again. Oh my God, take a look at the histogram we have now. When you want to compare the square root transformation, the cube root transformation, the log transformation, which one do you think that will work out of the three of them? It is the log. Look at that. This is looking, though not exactly like normal, but this is better than the first two transformational techniques. Okay, you can see that now. Okay, now, but let me tell you this. Whether you are using the square root or the cube root or the log transformation, okay, those are traditional way to handle that. But you know what? In a modern day statistical world, okay, we have, those approach have been improved upon. The approach of taking the log, taking the square root or doing the cubic, we have new approach that we basically call Tukey ladder of power transformation. Okay, so I'm going to walk you through that now, the Tukey way of transforming ANOVA data. And I'm also going to walk you through the Box-Cox transformation. Okay, so far so good, right? Is there anyone who doesn't really understand that? Is there anyone? You guys are good, right? Oh, those of you at the back, okay, thank you so much. Like I said, do not hide your feelings. You pay for the service, you deserve to be served better. And is everybody hearing my English, my accent? You're okay with me, right? Okay, thank you so much. Now, and I said, the approach of Tukey ladder of power uses a power transformation on a data set. For example, raising data to a 0.5, when you raise data to a 0.5, when I have y equal to 0.5, this is the same thing as square root of y. You know that, right? Which is y raised to power half, right? Okay, now raising data to a 0.33 is more or less this guy here, because this guy here is And this is like 0.33. Okay. Now it's equal to apply to that. Now, what we now want to do now, you know what Tukey did? Tukey now generalize this. Okay. Now when you transform with Tukey, all what you just need to do, you need to first load this package, arrow companion. Okay. Then you're going to write that. Look at that. Tukey, transform Tukey. What if you want to transform? You basically want to transform turbidity, you know, the turbidity data is skewed, right? Now, you know what I'm calculating here? Okay, the Tukey will give us the lambda. You know, this is why. This is I'm gonna show you something now. Okay, we wanted to believe that y is raised to the power lambda. We're looking for what is the values of lambda that can actually that will enable the data set to be transformed, right? Now, you know what Tukey has done here? Tukey is trying to tell us the lambda is minus 0.1. You know, initially we were trying what? Y raised to the power half, that's a square root, right? Y raised to the power 0.33, that's a cube root, right? But you know what? What Tukey will do, the Tukey will give us an optimal values of lambda, you know, that will make the distribution of the response variable to be normal. Okay, now take a look at that now. That actually give us that. And if you really want to know whether this lambda is something you can trust, you look at the p-value. Okay, you look at the p-value. Okay, the p-value here is a 0.08, right? The p-value here, you know, when the lambda value is going to work, okay, when the lambda value is going to work, the p-value should be greater than the level of significance. For the lambda value to work, it is not all lambda value that is going to work. Okay, now, based on this now, you know what I want to do here now? What do I want to do? I now want to plot the histogram after the data set have been transformed using the Tukey. Now let's see. Oh, that gave us this. That's looking like a normal. Even though we can't have a perfect normal. You get what I mean, right? Now, what I plotted right here is basically after transforming the data set, okay, using Tukey transformation. Okay, that is what I have. We don't have original data set anymore. The data set now has now been transformed. Now, what are we transforming? We are transforming the response. We don't transform the predictor. You know, in analysis of variance, right? We have the response. Response variable is continuous. The predictor variable is categorical. We don't reckon with the categorical predictor. We only focus on what? We focus on the response. Okay, now, you know what I want to do now? Let us now see what happened. If I want to conduct analysis of variance on data set that is problematic. What do I mean by that? Data set that have not been transformed. We want to use the turbidity now. Because you know what we want to do? We actually want to compare turbidity in different locations. Okay? We want to compare turbidity. Let me just tell you this. Some of you know Mississippi River, right? Mississippi River, to the best of my knowledge, it is not only in Minnesota, right? It's in other places. Now, what if in a situation where you want to compare turbidity, okay, in Mississippi River across locations? So I just wanted to be saying something like this, like that. Now, you know what I did? Now, when you look at that, before when you do the box plots of that, if you take a look at this, turbidity on location, you can see that we want to compare turbidity at different locations. Like I said, I wanted to be looking at it as a Mississippi River now, where you basically want to look at the water quality, okay, of Mississippi River. You now want to compare turbidity at different locations, and you don't even care whether there's a violation or not. And you now run analysis of variance. This is the result. What is it telling us? When you run the analysis of variance, okay, the data set is actually skewed. The data set is actually problematic. The probability distribution of this data set is not normal. You don't care, and you decided to run the analysis of variance. What do you see here? When you take a look at what you see there, you're going to see it is only significant at 0.05, right? But it is not significant at 0.01. We have two levels of significance. We have a 0.01. We have a 0.05. Okay, this is what we call 1%. This is what we call 5%. If you basically see that p-value now, you're going to see that that is greater than this, right? Which means the stupidity at different locations is trying to tell us they are the same, okay, at different locations, at 1%. But at 5%, it said they are not the same. But I want to tell you this, the data set that we use here, the response variable, the probability distribution of the response variable here is not normal, and therefore this result cannot be trusted. Does that make sense to everyone? This result cannot be trusted because of the fact that we ignore the probability distribution of the response variable, because the special requirement is that the probability distribution of the response variable should be what? Should be normal, but it is not. Okay, because of that, we cannot trust the p-value. Okay, what are we going to do now? Now, what we now want to do, we want to use the transformed data by Tukey. We want to use the transformed data by Tukey. And you know what? We first draw the box plot. Here we are considering 3 locations. We want to compare stupidity in 3 locations. And the box plot that I have here, this is after the data set have been transformed. What do we use? We basically use Tukey to transform that. And let us now see, let us run analysis of variance. Oh my God, take a look at the result. This one now is, I want you to take a look at what I have here, this stupidity underscore talk. Okay, we've already transformed. Let me show you how that is transformed. You're going to see stupidity under, do you see, I'm going to show you now. You're going to see how that is transformed. Do you see this guy here? Do you see this guy here? We are using that response now. The response variable that has already been transformed now, and we now run the analysis of variance on that. I'm going to show you what we got. Look at the p-value now. This is very, very small compared to the one we have before, before transformation. If you take a look at the p-value we have here now, this is only significant when the level of significance is 5%, and it is not significant when the level of significance is 1%. Now, but if you take a look at this one now, after transforming the data set, oh my God, look at the p-value now. This p-value now is less than any reasonable level of significance. Then we can trust this. You know why we can trust this guy here? We can basically trust this guy here because the probability distribution of the response variable is normal. And let me tell you this, if the probability distribution of the response variable is normal, automatically the probability distribution of the residual will be normal. And that is the reason. Now take a look at that. Now, we now decided to investigate residual. Let's see, based on this. Oh, what did I tell you? I told you, what I'm trying to show you now is the histogram, okay, of the transformed data using Tukey. You can see it is normal. Take a look at that now. Okay, I told you before the probability distribution of residual can be normal, then the probability distribution of the response variable has to be normal. Okay, now I now try to look at the normal KK plot. Oh my God, this is looking so great. The normal KK plot is looking so great. Now, that is how to use a Tukey transformation for ANOVA data. Is there anyone, before I go to the Box-Cox transformation, okay, is there anyone who want to ask question, who need clarification before I go into a Box-Cox transformation? Because we just finished the Tukey transformation for ANOVA data now. Is there anyone who need clarification, whether in person or online? Those of you online, can you confirm if you are hearing me? I need someone to confirm if you're hearing me clearly.
Yeah, we can.
Oh, okay. Thank you so much, and thank you for confirming that. Is there anyone among you who want to ask question or who need clarification? Okay, if you guys are good, I needed to say yes, or you comment yes if you guys are good with my explanation.
Yes.
Okay, thank you so much. But you know what? If there is anyone who is not clear and you cannot disclose that right now, I need you to send a message to me. I'm going to sit you down one-on-one. Now I'm going to explain to you. Please reach out to me. Okay, take me as your friend. Reach out to me. Okay, now that is going to be the end of the Tukey way of transforming data, but we have another way of transforming data. I want to talk about Box-Cox transformation. Okay, you know, whether you use a square root transformation, a cubic root transformation, a Box-Cox transformation, or a Tukey transformation, all what we're looking for is a way to make sure, let me tell you this, when the probability distribution of the response is normal, the probability distribution of residual is going to be normal. You know what is going to be the implication of that? The p-value will be very, very small. I'm going to say that again. When the probability distribution of the response is normal, the probability distribution of the residual will be normal. And the implication of that is that when you run an analysis of variance test, you're actually going to have a very small value for p-value. And that's what we want. That's basically what we want to see. That different exists. Okay, now I want to do a Box-Cox transformation now. Okay, and in a Box-Cox transformation, you need to load a package called mass in R. Okay, and this is what are we transforming? Don't forget, we are transforming stupidity, which is the response, right? And if you want to do this, you can choose a sequence, okay, from -6 to 6, and it's 0.1. Then you're going to do cos, that are your frame, Box-Cox X and Box-Cox Y. And at the end of the day, we're basically going to have, you know, the difference between the Box-Cox transformation and the Tukey transformation. The Box-Cox transformation will do it for both X and Y. In the Tukey transformation, we only focus on just one variable. But right now, take a look at what I have. It's doing it for the two. And at the end of the day, you're basically going to see here, you know, here we're going to get a lambda, and we're going to put a lambda, you know, say stupidity raised to power lambda minus 1 divided by lambda. And where is the lambda coming from? The lambda is basically coming from here. And when we draw the histogram again, let's see what we have. This is the histogram after using a Box-Cox transformation. Okay, you know, in statistical analysis, we can compare transformation and effort. We basically want to say which one we attain normality. Okay, now this is what we have now. Now the next thing that I actually want to do now is I want to look at the bus plot. Okay, I want to look at the bus plot of that after using the Box-Cox. This is what I have. Okay, this is a box plot of the 3 locations. Okay, after using the Box-Cox transformation, then you know what I want to show now. I want to look at the analysis of variance. Okay, after using the Box-Cox transformation. Oh my God, look at the p-value. The p-value is 0.0047. There's something I want you to see now. When we did not transform the data, right? The p-value that you got is different from when you transform the data with Tukey, and the p-value that we got now is 0.0047, is also different from when we transform with Tukey. Now, if you take a look at what I have now, when you look at the p-value that we got for the Tukey transformation and for the Box-Cox transformation, you're basically going to see that the two of them are less than 0.01 and 0.05. If you take a look at that. Okay, therefore the Box-Cox transformation and the Tukey transformation, they're basically telling us the same thing. Okay, I wanted to look at that. You can also do the residual analysis, okay, and see whether this is a residual, this is a histogram of the residual using the Box-Cox transformation. You can also look at the normal QQ plot using the Box-Cox transformation, and that is basically what you're going to have. Now, today, I actually walk you through different type of transformation, and you know what? We only need transformation when there's a problem. Problem of what? Problem of normality. You basically know how to investigate that when you have analysis of variance data, or what you just need to do. What is the histogram of your response variable? And you can do the Shapiro-Wiley test of normality on that. The moment the distribution of the response variable is not normal, okay, then you need to transform. You don't go ahead and conduct analysis of variance. I want to say that. I'm going to say that again. Our models are not failing us. We are the one that we're not doing the right thing. Okay, we need to do the right thing by investigating whether assumptions hold or not. Some researchers don't care about that. They ignore that. Okay, when you ignore that, you ignore reality. And when you ignore reality, your model can never stand the test of time. And that is the reason why at times we have problems. Now I'm going to go into the conclusion now. So what did I say? Both Tukey ladder of power principle as implemented by transformed Tukey function and the Box-Cox procedure were successful at transforming a single variable to follow a more normal distribution. You can see from what I've demonstrated to you. I first started with the traditional way of transforming data. That doesn't work. Okay, I started with the square root, with the log, and so on like that. But you know what? The modern day transformation is actually going to be between Tukey-transformed technique and the Box-Cox technique, because you know why? They're always going to achieve normality. And that's why you can try them. Now, I said they were also both successful at improving the distribution of residual from a simple ANOVA. Let me tell you this. The moment the probability distribution of the response variable, I repeat, if the probability distribution of the response variable is normal, then the probability distribution of the residual will also be normal. I just wanted to take note of that. Okay, now I said the Box-Cox procedure has the advantage. Let me now tell you now. We've used a Tukey, we use a Box-Cox procedure, but the Box-Cox procedure has the advantage of dealing with the dependent variable of a linear model, while the transform Tukey function work only for a single variable without considering other variable. You remember, I showed you for the Box-Cox, it considered both the response and the other variable. But the Tukey only focus on a single response alone. Okay, now, and that was why I said because of this, the Box-Cox procedure may be advantageous when a relatively simple model is considered. In cases where there are complex model or multiple regression, you know what I mean? When I have more than one factor, then it doesn't make sense using a Box-Cox. Situation where you have more than one factor, I think I will advise you use only Tukey. You know why? Well, what Tukey will do? Tukey will only transform the response alone. But the Box-Cox is only advantageous when you only have one predictor. Here in this example, the predictor is location. You know that, right? Okay, so that is it. So now I said in cases where they are more complex or multiple regression, it may be helpful to transform both dependent and independent variable independently, but using the Box-Cox, that would be more kind of tedious. Okay. And let me tell you, you may not necessarily need to transform predator variable to achieve normality. The moment you transform the response, you could be good, but you have a way to check for normality. Okay, that's going to be the end of my lecture today. Is there anyone who need clarification on how this transformation? And before I go today, I want to hear from you about the lab, about the way the lab is conducted. Okay, thank you so much. About the way the lab is conducted. If you don't feel satisfied with the way the lab is conducted, please reach out to me. I'm actually gonna, call my TA, where I want everyone to be served better. And not only lab, if you're not satisfied with the way assignments are graded, if you feel that your assignment is not graded fairly, because my TA grade assignment, I grade exam, I want to hear from you. I don't want anybody to be cheated. Okay, does that make sense to everyone? Okay, do you have any question before I go? Okay, go ahead. Oh, okay. Okay. Yeah, somebody said I should go back to something. Give me 1 second. I'm gonna do that now. Oh, okay. I think let me force yeah. Oh, okay. So you mean you cannot record the data set, right? Oh, you can. Okay, I'm gonna look into that and see what I can do on that. So thank you for informing me on that. Uh, let me put that again. Yeah, it's gonna come on now. Okay, so is it on Box-Cox, right? Okay, is it right here? You're welcome. Oh, okay. Yeah, actually, what actually happened is this. Uh, if on a normal ground, let's say there's no problem, maybe it's supposed to be significant at all level of significance. And because of the problem, it's only going to be significant at one level of significance. And in some situation like some that has to do with life, like medicine, at times they require high level of confidence. So the high level of confidence is when the level of significance is 1%. In fact, it even depends. I have some data set where it's not even significant at all at 5%. That depends on the level of violations. That's what I mean. So in most of the situation, we normally have a kind of it normally change decision when the response variable is problematic. And that is the reason why we care to investigate whether the distribution of the response is normal before we can go ahead and do and conduct ANOVA analysis of variance test. Yeah. You're welcome. Okay. Oh, let me just end this first.